If you want to get a clear view of what the sun's doing, you have to get above the Earth's distorting atmosphere. So we use satellites to gather the data that we need to understand how the sun works. The sun radiates at all energy levels. Radiation is energy that travels and spreads out as it goes. There are different types of radiation. Let me show you. Visible light that comes from a lamp in your house, or radio waves that come from a radio station, are two types of radiation. Other examples of radiation are microwaves that cook popcorn in a few minutes, infrared light, which restaurants use to keep food warm, ultraviolet light, which causes our skin to burn, X-rays, which help doctors look at your bones, and gamma rays, which are emitted from radioactive materials. So, Jennifer, let's apply this information to the sun. As Eric stated earlier, the photosphere emits energy primarily in visible light, while the lower corona emits energy in extreme ultraviolet light and the upper corona in X-rays. By zeroing in on one particular light energy, we can study the various parts of the sun and how they interact.
Okay, Dr. Odenwald, how can satellites help us to monitor and observe the sun?
With satellite technology, you can look at the sun 24 hours a day. We can put satellites outside of the Earth's atmosphere to collect valuable data from the sun and to act as early warning devices against solar storms. 3 important satellites that monitor the sun and provide us with real-time data are the SOHO, ACE, and IMAGE satellites. If you'd like to learn more about the SOHO satellite, Dr. Terry Kuchera, one of our researchers at NASA Goddard, has all the information.
Great. Hey, Terry.
Hi, Jennifer. SOHO, or the Solar and Heliospheric Observatory, has a dozen different instruments which observe the sun 24 hours a day without interference from the Earth's atmosphere. These instruments record the activity of a solar corona, the photosphere, and even study the sun's deep interior. SOHO has telescopes on board that take pictures of the sun in ultraviolet light. Also, SOHO can give us a 2 to 3 day early warning of coming solar storms that can affect the Earth's magnetic field.
That's really cool. Thanks, Terry.
Oh, you're welcome.
So what's next, then?
The second satellite is ACE, the Advanced Composition Explorer. ACE operates like an ocean buoy that measures the density, temperature, magnetism, and speed of the solar wind as it passes by. If a solar storm is headed our way, ACE will detect it and give us 30 to 45 minutes warning that a storm is about to hit the Earth.
Cool. So how do NASA researchers then analyze and interpret the data?
One way we can analyze and interpret data is by graphing. The graph shows the speed of the solar wind changing as it blows by the ACE satellite. The title of this graph is Solar Wind Speed. The horizontal axis, or x-axis, represents the number of days in September of 2000. And the vertical axis, or y-axis, represents the speed of the wind in kilometers per second.
Okay, Sten, it looks like the speed of the solar wind ranged from 350 kilometers per second to 800 kilometers per second during the month of September.
You're right, Jennifer. On September the 18th, the solar wind reached speeds of 800 kilometers per second, or about 1.7 million miles an hour. But most of the time, the solar wind averaged around 450 kilometers per second. From the analysis of this graph, we can determine how long it took the solar wind to reach the Earth's atmosphere.
That's amazing, Sten. Now, besides SOHO and ACE, you mentioned a third satellite, IMAGE. Is that the one you're working with?
That's right, Jennifer. IMAGE, which means Imager for Magnetosphere to Aurora Global Exploration. And it's a satellite that orbits the Earth and measures the locations and changes in the invisible clouds of particles that surround the Earth in space. You probably already know one of these cloud systems, the Van Allen belts. Astronauts and satellites avoid these belts because of their radiation hazard. There is also a separate collection of particles called the ring current, which appears and disappears whenever the Earth gets whacked by a solar storm. Another one of these clouds, called the plasmasphere, is actually a part of our own atmosphere that extends over 10,000 miles above the Earth. The IMAGE satellite lets us watch these different families of clouds change. IMAGE helps us understand how solar storms can cause problems for our technology in space and the health of our astronauts working there too. More importantly, it helps scientists improve our ability to forecast space weather.
Wow, I realized the sun was critical to sustain life here on Earth, but I guess I never realized the devastating effects the sun could have on us.
It's amazing, Jennifer. Solar storms have caused billions of dollars worth of satellite damage in the last 20 years. They have caused blackouts and will always be a hazard for astronauts working in space. Satellites like SOHO, ACE, and IMAGE, and their replacements, will be our only means of keeping track of when the next storm hits Earth's magnetic field. If students would like to learn more about how the sun works and about solar storms, they can visit the Sun-Earth Day website, which was developed by the Sun-Earth Connection Education Forum, in collaboration with the NASA Office of Space Science.
Thank you so much, Dr. Odewald.